these are some type of some type of membrane. And these membrane, if you see water, okay, so if you see the water can be passed through, because water has the hydronium ion inside the water can be easily passed through with most of the membrane. And if you want to selectively take out the ions from the waters, it's like S3O plus, S3O plus, then we need to use reverse osmosis method, and we have to make a membrane in form of ion exchange, so that ions can be withdrawn from that membrane. So and if there are monovalent, multivalent ion, then we have to use ultrafiltration and nanofiltration method. Similarly, like bigger particles like viruses and protein, we can use microfiltration and particle filtration if we require. So we can use pore size membranes. So these are the things. And if you take a current example, when this pandemic happened, and all this protein and viruses were studying. So most of them studied carried out through this membrane technology only. All this required protein has to be absorbed through the membrane, and the rest all the filter out through that. So these are the things. But here, what the interesting thing what I want to mention here, I'm not covering everything here, but our group work on this, all this system. We are running several projects from different big companies, and we are making different types of membrane for them. But here I will be talking about this section, the ion exchange membrane, particularly this one, not sorbent, the ion exchange membrane for energy application. So as I mentioned, like energy is also very vast field, big field. It's not like there are several sections inside that. And there is a big scientific community for energy device, and where there are so many societies are also there, like electrochemical society, like MRS society. They are big societies, and they are focusing on electrolytes and membrane, ion exchange membrane. So this field, the field which I have been, the membrane field which I have been talking about here, and the energy field is like both big field. But here I'm just telling you about how they are merging it up. So in my next slide, if you see how these ion exchange membrane can be utilized inside the energy application. So these are some devices, the next generation electrochemical devices, and most of them use such type of ion conducting membrane or polymer electrolyte, or solid polymer electrolyte, or liquid polymer electrolyte. So if you see, these are the common used electrochemical cells. So first structure is like first structure is supercapacitor, and like battery. So these are used for storing energy, and for generating energy, these solar cell, fuel cell, reverse electrodialysis. This is an electrochromic fill, which is generally used to avoid ultraviolet rays. So if you see the structure of all these devices, electrochemical system, the physics behind all these devices is a little bit close to same, but in some other way, the principle is of this architecture differs. So if you see here, in the case of supercapacitor, there are anode, cathode, and when they generate some, through electrochemical reaction, they generate some current, so it can be drawn from the current collector. So many people have been working here. Maybe you are also, some of them viewers also been working on such type of system. So the focus is not to design this architecture, because many group have been working here. The main focus of my group is to fabricate or understand what is happening behind ion conducting membranes, or the membranes which can be utilized. Our target is to make an ideal type of membrane which can be utilized for these operations, the operations inside these devices. Similarly, this is a solar cell, like a dye-centralized solar cell, and here counter electrode and ETL has been used to generate junction, and from that junction, the electron and hole pairs are generated, and those are being transported through outer circuit, and when they come again, then hole, and which has to pass through this electrolyte. So if you see here, these yellow portion, these are the electrolyte which we are talking about, that, and that can be also replaced by, or most other devices are working on ion conducting membranes. So similarly with electrochromic display and electrochromic device and these batteries, and this is fuel cell. Here also that graphitic plate is sandwiched between that ion conducting membranes. When hydrogen and oxygen has been pure as a fuel, so it converted into energy and water. And here this is the reverse electrodialysis setup. And in this reverse electrodialysis setup, what we are doing, like we are taking salinity gradient of high concentration water and low concentration water, and we are producing energy through the salinity gradient. And that salinity gradient generate potential, and that from that potential we extract energy out of that. So in all this electrochemical cell, if you see what they are doing, they are generating charge. They are generating that charge has been converted into electrons, and those electrons producing energy. So it looked like very easy to, and it looked like very simple, that just make an electrode, cathode, anode, or and then just place our polymer electrolyte or liquid electrolyte or ion conducting membrane in between them, and we can get the energy. It looked like simple, but there is a lot of chemistry going on, and here I'm just going to not talk about the chemistry part. It's not that simple, because if you take the example of battery, lithium-ion battery, the cathode, anode, and when they generate charges, so what happened? The charges has to pass through this polymer electrolyte or any liquid electrolyte or ion conducting membrane. When they pass through this membrane, what happened? It weakens the interface, and that can be crucial for damaging this structure, and it can result into severe consequence. So our target is to make a strong and reliable system which can make a stable system. If we are not using such type of membrane, or means a strong membrane, or if we are using something like fragile or some system, so these electrode, like if you see anode and cathode electrode, can get shorted it out, and it can generate a lot of heat, which can result into fire. And this is one example with lithium-ion batteries. This is happening with fuel cell also. So if we not take into, if you're not idly making the system, idly making electrodes and the membrane, so the membrane can be damaged and the electrode can be shorted out and leakage can happen. And as everybody know that hydrogen is very highly inflammable. Similar with other devices also. So if intermediate is not working well, the efficiency will go down. So these are the things which are the drawbacks. So how to cope up with this? So how to reduce this, and what are the if we see the present the the devices which has been made and which has been used by consumers, they are facing a lot of problem, and most of the people also heard this thing, and I will show in my next slide what this problem is, and this is a serious problem. And if you see in this slide, these are some electrochemical system, especially batteries and fuel cell, which has been like failed. And these are the big companies and which are pioneered in their technology, and they promised it will serve the mankind and there will be no consequences, but they failed. And uh, the work which we are proposing here, what we are doing to replace, to make a material which can be reliable, which can be trustworthy, and which can be safe. So in this direction we are working, and we are targeting that this type of incident can be like avoided. So this is just a consequence slide. And this is the latest. All these are the latest incident which has been happened around the globe through these electrochemical cells, different type of electrochemical cell. To understand how this is happening, what is the reason behind it? First, we need to understand electrolytes, what causing this problem, electrolytes and electrodes. So, but here my specialization is an electrolyte, so I will be talking more about that. So as I mentioned earlier that shorting of these two electrodes, or cathode and anode, is a major problem. So this can be avoided if we make a strong and stable and high conducting material, high conducting membrane. So this can be avoided. So at present, most of these systems which are highly efficient use some liquid electrolyte or solid oxide material. So if you see the next slide, which talk about the different types of electrolyte. Here, the first category, if you see, inorganic solid electrolytes. These are like highly safe electrolyte, but it's not efficient, and they are poor cyclic stability. Means they are not practical that much, but still in some places, in some research, they are showing some promising result, and still research is undergoing. At present, liquid electrolyte has shown a lot of promises, but as we have seen from the previous slide, safety is a major concern with the liquid electrolytes. And most of the research and most of the industries are targeting to replace this liquid electrolyte with something like a polymer type of electrolyte. And polymer electrolytes has been categorized, if you see, in these three categories: gel polymer, solid polymer electrolyte, and this is polyelectrolyte. Means this is a polymer electrolyte, this is a polyelectrolyte, is an ion conducting membrane. So this is another name of polyelectrolyte, you can say, and this is a topic of this presentation also, ion conducting membrane. So gel polymer electrolyte, these are flexible, multifunctional, chemically stable. but that does not have a good mechanical strength. The tensile strength is very poor, so it cannot give a stability to this devices. So, but still they are doing good, and they are solid electrolyte, solid polymer electrolyte, highly flexible, thermally and chemically stable, multi-function, mechanically stable also. As comparison to gel electrolyte, they are a little bit stable. But conductivity is not that good. But they are also, because there are more than 20 to 30 companies around the globe, which through survey I came to know that they are making different types of devices for electrochemical devices, and they are doing pretty good. Like there are many solid polymer electrolyte companies which are make their product toward the commercial end. And this category, the ion conducting membrane category, is like the conductivity is good, mechanical strength is good, chemically stable, and highly flexible. But if we talk about the stability under stress condition, they could not perform very well under stress condition. Like the thermal stability is not that efficient, and although the conductivity, which they most of the work has been performed at elevated temperature, they are performing very well. But at room temperature, conductivity is not that well, but it's reasonable. I mean, the interesting thing is that these systems are safe, and some companies are using these systems. Like here in Seoul, there is a Hyundai and Samsung display. They are using this technology, and although these are at the prototype, or there's some not in larger scale they are using, but I have seen that so many big companies has funded many projects in various industries and various universities or research institutes. So these are the different types of electrolytes, and we are focusing here and like ion conducting membranes. So how we can know that which electrolyte we have to use, and what in which devices. So if you see next slide, here is the criteria we are seeing. And first we need to see it should be low cost. The material should be low cost. It should be non-toxic, and it should be safe, compatible with electrode. Means it should be not like there should be grain boundaries between electrode and electrolyte. So there should be compatibility, should be good. High dielectric constant should be there, and excellent charge and storage capacity should be there. And the initial parameter when we prepare any electrolyte and prepare any ion conducting polymer, we measure conductivity of that, and from there we get the first characteristics, whether it's going to work inside our system, or not, whether it's reliable or not, whether it is good system or not. So if we see, these are the different types of electrolytes, and here in one chart I have shown here. This has been created with a lot of data, reported with literature, and some data are from industries. If we see the liquid electrolyte, is the conductivity is above -3 order, and which is like this is our target. This is the target for many industries and many research groups. So they want their electrolyte to be above -3 order Siemens per centimeter. And this is the like, but as I mentioned earlier, that liquid electrolyte cannot sustain, and the safety is a major concern. So solid polymer electrolyte, gel polymer electrolyte, single ion conducting electrolyte. So these are relatively low ionic conductivity. They show very low, but these are the solid oxide electrolytes, as I mentioned here. These are the inorganic solid electrolytes. Still, some system has been reported. They are promising like sulfide electrolytes. They have reached to the commercial level also, but the conductivity is not that enough. And some only few systems they can show good conductivity, but in long run and it's not performing that well as comparison to the liquid electrolyte or solid electrolytes. So if we see single ion conducting electrolyte, this system and this polyelectrolyte system is almost same. The basic element, the organic element is same, but they conduct lithium ion through the membrane. But in polyelectrolyte, that is anion exchange membrane and cation exchange membrane, they conduct hydronium ion like H+ and OH-, and their conductivity is very, if you see, it's very high, and which is like this is due to the hydrated state, because most of the polyelectrolyte which has been used in fuel cell and redox flow batteries or the electrodialysis system, so they are in hydrated state. So at one platform it looked like they have very high ionic conductivity, but if we talk about at room temperature, they will show relatively low. So that's why this class is different from lithium ion class. So they transport lithium ion, and these electrolyte transport hydronium ion. But here the presentation is focused on this type of electrolytes, like which ion conducting electrolytes. These are the ion conducting membranes. Ion conducting membranes. So basically, ion conducting membranes are like an ion exchange membrane, cation exchange membrane. Most people know this. So an ion exchange membrane means anions are being transported through the polymer network, and cations has been blocked. So in cation exchange membrane, cation will be transported through the membrane, and anion will be blocked. But if we compare, if we see these system, these follow like anion cation both moves towards the cathode and anode. So in this system, both anions moves. In single ion conducting, only one cation or either an ion will move. So here is a lithium ion. So lithium ion moves and cation will be fixed. But in these systems, both anions moves either side. So when it's charged, so from anion move from cathode to anode, or cation move anode to cathode. Similarly, vice versa when it discharge. So I think people understand, means we were understood that what is the main difference between single ion conducting and polyelectrolyte, anion exchange membrane and cation exchange membrane. It look interesting that this wide class of polymer electrolyte, and it look easy to select a particular type of electrolyte. But if we talk about the polymer science or polymer chemistry behind that, because Selecting ion is not the choice, because particular instrument require particular type of ion, because these are the more efficient ions. Because for the lithium ion batteries, we know that lithium has been like most promising ion, and it generates a lot of energy as comparison to sodium and other batteries. So similar with like fuel cell and other electrodialysis system, we know that hydronium ion is the most promising ion. And if we talk about the other methanol and other fuel cell, in that case also, we know that polymer structure plays an important role in governing those ions. And so particular application require different type of matrices, so that we can make an efficient system, efficient membrane out of that. So coming to the physics part, like polymer physics or polymer science part. So what we are doing here, we are engineering the polymer structure, and we are governing these ions. So we are suppose if we are making a system for fuel cell or lithium ion battery, so we choose particular type of polymer, and we design in such a way that can make a path for particular ions. So if you see the next slide, so here we are polymerizing different type of polymer, like speak, Nephron, polysulfone. So here different structure I have presented here, and if you want to read into the depth of this polymer chemistry or the controlled polymerization process, here this is a paper which has been cited here. So this is one of the paper, and if you see the beauty of this polymer chemistry, there are different types of structure, and we can play with them, and we can make according to our need. So if you see homopolymer, which are like strongest polymer structure, and we can branch them, we can connect functional group inside that, and we can target our anion or cation to move inside these polymer structure, and we can control the diffusion coefficient of ions, and we can also make a efficient system out of that. It's efficient system, safe system, reliable system by doing this polymer chemistry. So if you know that recently Professor Sharpless got the Nobel Prize for this, doing polymer chemistry only, the click chemistry. So it's like 2 times he got the Nobel Prize. So these are the things which we are doing in our laboratory, and we are preparing different structure polymer, and we are attaching anion or cation inside that to the branch of, suppose here we are attaching some cation or anion and making it transport counter anion through that. So these are the things. So to understand how it works, so we need to understand the mechanism part of this, like how this anion or cation has been transported through this polymer chain. So if you see the next slide, that will talk about the ion conducting mechanism. This is a simple mechanism. If you see, this is a lithium ion, the yellow one, and it's been attached with it. This is a theoretical model which has been prepared, and it will be attached with the negative sign, that the oxygen molecule, and these are the distance which has been recorded through this molecular dynamics simulation. And if you see this lithium ion is transporting through this hopping mechanism, like interchanging hopping mechanism, and so like this, the conduction happens in the simple crosslink type of system. But if we are doing some engineering part, like as I demonstrated here, what we can do, like we attach like anion at the, we are fixing this anion at the one side, or we can replace with the cation also. It's up to our hand. So what we are doing, we are fixing anion and we are making it to pass counter anions or ionic species. And this gives flexibility to control the conduction, control the mechanical strength, control the many properties we can control as much as we are making system like this. So these are some examples, other examples also, but here, like here, there is no pendant type of network. Here, if you see, there are pendant type of network which give the like rotational motion or segmental motion of the polymer chain. So these are the things which we are doing in our laboratory, and it looks fun. So in the next slide, if you see, this is another paper which is also talk about a similar thing, but it's a cross-link system. Like we are taking polymer and we are cross-linking their networks and making a path between them by incorporating bulk material inside that, and then through interchain hopping or interchain via cluster hopping, the ions are moved. But this mechanism is typical with the mechanism which we have demonstrated here. But this mechanism is totally different. It's based on like a Groth's mechanism, and it's pretty, it's like reliable as comparison to this. But both systems are doing very well in our device, and these both systems have shown some reliable result also. And here, I have shown that there are different sites how anion cation depends on the different defects inside the whether it's like a crystalline network or polymer networks, because polymer are composed of crystalline and amorphous material. So those region has been defined. If it is a crystalline region, so there will be an anion and cation vacancies, and there will be grain boundaries or phase difference between that. And ion moves from these phase differences and grain boundaries very efficiently. But if we control, if we control all this anion or the counter ions, if we fix them, then only one species will move, and that we need for our system, because then both anion will not polarize at one side. Only one anion will be moving at the either side. And it gives stability to the system also, because the framework which we are talking about is strong as comparison to the other system. So with this mechanism, with this material chemistry, we make this such type of membrane, and many universities are working on related to this field. So here are some reported literature, and if you want to see other groups' paper, so here, if you see this, you can refer to this paper. This also talk about this type of all the freestanding ion conducting framework or membrane, which has been prepared with the physics or the chemistry which I have talked about earlier. So all these membranes which has been demonstrated here has been prepared with those polymer chemistry. And it looked like a similar to like a conventional solid polymer electrolyte, but it's totally different. The chemistry part is totally different, and the mechanism is very reliable. Now, after preparation of such membrane, we send these membrane for the fabrication of devices to industries and to other laboratories. And normally, as I mentioned, that there are several types of electrochemical devices, electrochemical cell, but I will be just talking about a couple of them so that viewer can see what and how they can use this system into their devices or their infrastructures. So here, if we see, I will be talking about reverse electrodialysis and fuel cell and how we are using such membrane inside them. Or these membrane can be used inside any electrochemical cell, like fuel cell, batteries, like supercapacitor, like dice and trisolar cell. So here, if we see to make this ion conducting membrane, one should look into these parameters. It should be uniform thickness. Thickness should be maintained very uniformly so that ideally it can transport the ions from one side, one electrode to another electrode. Mechanical strength should be high. As I mentioned, the mechanical strength of these polymer chemistry based membrane is very good as comparison to the conventional membranes. Purely chemically inert, it should not react with the electrodes which are present inside that. And swelling should be low because at hydrated condition, because these system work on the at means moisture level, means RED, reverse electrodialysis, like as I mentioned, that work on the salinity gradient. So there is a high concentration water, there is a low concentration water. If you want to take the example, I will give the example like a sea water is like saline water. River water is less saline, means it's not saline. So intermediate of that place, we can install this type of devices and we can generate energy out of that. So likewise with the fuel cell, means when hydrogen and oxygen are reacted in between interface of the electrode and the membrane. So water and energy is generated. So that water can be responsible for the swelling, and here salinity and water can be responsible for the swelling. So this has to be taken into consideration before. This is the crucial part of this type of membrane. So if we control the chemistry part, so we can control this swelling part also. Readily flexible membranes are very flexible, as I show here. These are the very flexible membrane. This cannot be unique. Means the tensile strength is around 60 to 40 megapascal. So toxicity should be low and low degradation. So if you see, these are some parameters we look into before finalizing any membrane. So conductivity is one parameter. So we target our conductivity 0.1 Siemens per centimeter at 100 degrees Celsius. This conductivity which we are talking about at 100 degrees Celsius, at 100 relative humidity at 100%. So at 100%, this much conductivity means this high conductivity we have achieved. Means it's not like only we have achieved, many groups have already achieved. So the activation energy, targeted activation energy should be as low as possible, like below 10. And ion exchange capacity is another form of, you can say, conductivity, because conductivity and ion exchange capacity is directly proportional, and it should be below 2. It should be around 2, because if we increase the ion exchange capacity, the membrane can lose its structure, and it can easily break. So that we need to consider. And water uptake should be low, and that tensile strength, as I mentioned, is like above 10. And if it is very high, then it's good. But with this type of system, the system which has been reported earlier is around 60 megapascal is quite fine. Means it is fine to work with any commercial level devices. So these are the things which we take into consideration when we are developing any system or when we are developing any membrane. But there is, it's not as cool it look like, but because there are some challenges what we are facing with it. Because if you see the parameter, if we increase the ion exchange capacity, the conductivity also increases. But as here target is to increase as much as conductivity. But the problem is when we increase the ion exchange capacity to a certain level, membrane loses its structure, and like swelling is the major problem arises. So if you see, these are some. In next slide, there is some result which has been shown from our lab. So the membrane which has been designed, which are in dry state, it was like very, very flexible, very good membrane. But as under hydrated condition at elevated temperature, it swells like this much. And this type of swelling is not good for our devices or any electrochemical cell, because this can damage the device as well as the system. Because this much swelling can be makes our system very fragile, and it can easily break the interface between electrode and electrolyte. So these are the parameters we need to see before finalizing any membrane. So as you can see that if the swelling increases, the tensile strength become weakened, and the thermal stability will also lose, because at high temperature these cannot be sustained, and the reliability issue will arise, and compatibility within electrode will be not good. So to avoid this thing, we are doing some polymer chemistry to make more strong membrane. And there are other alternative ways also, like in couple of system we have introduced some filler to tackle with this problem of swelling inside the membrane. So in one system I will talk about here. Here what we are doing, we are introducing some single wall carbon nanotube, because it has been well reported that single wall carbon nanotube is very strong, with the mechanical strength is very high. So we are introducing inside that, and what we are thinking that it will give the stability to the membrane. But interestingly, we have found that introduction of a single wall carbon nanotube provide the path for ions to also to travel through those channels, that the path which I have is shown in the previous slide. And here are some parameters which we are taking into consideration for measuring all these things. So as most people know that, conductivity depends upon like number of charge carrier, mobility. These are the two main parameters. And the type of charge, the Lewis type of charge, whether it's positive or negative. So here, if you see number of charge, either we can increase the number of the charge carrier inside any membrane or polymer electrolyte, or we can increase the mobility. Either way, we can increase the conductivity or ion exchange capacity of that. As we have seen that increasing the ion exchange capacity, it can make our system fragile. So that one need to take into consideration. Here are some formulas I have mentioned. Uh, if we are calculating this like if we want to understand how this number of charge carrier and mobility plays a dominant role, so we need to calculate the diffusion coefficient or diffusion value inside this membrane or inside this polymer electrolyte. So here are the three methods popularly most research group are using. Either we can calculate the macromolecular segment of polymer. That can give you the as I show here, if you measure the segmental motion of these ions, that can give the diffusion coefficient. And or through NMR, we can also calculate the diffusion coefficient. And through EIS, I think Dr. Noor is expert in this. And here from this also we can calculate diffusion coefficient, and we can understand what is going inside, how these ions are playing a major role for the conduction. Similarly with the electrodes, also we can calculate using Arrhenius equation or the diffusion coefficient of the. But overall, through the research, we have seen that these are just estimated values, the theoretical values from the experimental data. But relying on the is not very much efficient, we have observed that. So but we will get the clear picture what is happening inside the system, or what is happening inside the ion conducting membrane or the polymer electrolyte. So these are the things. So in one, there are several type of system we have prepared, and we have calculated what are the roles with whether number of the charge carrier is dominating or whether mobility is dominating in our system. So in our next slide, if you see here, these are the different types of system, and what we have seen that introduction of ions, if to a certain level, number of the charge carrier plays a dominated role. After high concentration of those ions, mobility plays a dominated role. This has been evaluated from this diffusion coefficient values. So it looked like this gives the clear picture what is happening behind these membrane or polymer electrolyte system, and we can study the physics behind all this ions and polymer structure through these equations which has been mentioned here. So some calculation can be done through like manually, or some require some good MATLAB or some other software to evaluate all these parameter for this equation. So this was the thing, and after getting this estimation, one can say that till where we have to increase the concentration of ion, and where we have to stop that, and till how much we have to put the fillers, or to how much we have to strengthen the material using other materials, other organic or inorganic materials. So this gives means this using this approach means one can easily figure it out, like one can easily understand what is happening inside any system. So this was the thing. And if you see after introducing a single wall carbon nanotube inside this, so what we have observed that these are the long single wall carbon nanotube inside the polymeric system. What we have seen that when means as a pristine Nephron membrane, which has been the like ion conducting membrane, their tensile strength was very good, and their strain was also very good. They are flexible membrane, but after introduction of this single wall carbon nanotube, it become little brittle, and the flexibility get loosened up. So this we have also need to consider before, because we cannot introduce as much as we want, means because they are damaging the polymer structure. So a few means less amount or like limited amount can work very well, but excess amount will destroy the system. This was after this was also confirmed through some molecular dynamic simulation. Also, we have performed on this. So in next slide, if you see through here, you can see this is a system of salinity gradient. So here is the river water, seawater. Seawater has high concentration of salt, and this has low concentration of salt. So ions should be moved from high concentration to low, and this is the carbon nanotube, single wall carbon nanotube setup. And here yellow portion is said to be a functional group of cations which has been moving, which makes ions to move through them. We found that the flux between the, we have calculated the flux intermediate from this carbon nanotube, and we found that there was promising results, and those flux was like but transporting only single type of ion. So this was one of the good result which we have seen. And similarly, what we have done that when we are introducing these fillers, and we found that some agglomeration also taking place inside that. So this is due to the crystallization of particles which has been taking place. So what we have done, we made amorphous particle, and then we introduced inside this, and we found that mechanical strength of what we were losing out was maintained, and the strain value is almost the same what we are getting in the pristine one. So these are some results which has been simulated through molecular dynamic simulation, that if the channel size has been limited, it has been increased to 6.3, which is giving a stable result. And if you see the result which has been obtained, both the filler one and the non-filler one has a stable performance, and still 20 hours we have measured. And here we have shown that to a certain level of means introduction of the filler can increase the conductivity, but after that it gets saturated. So extra filler can damage the mechanical strength also, as well as, and it will not leading to the enhancement of conduction or other things. So these were some result, and as I mentioned that the mechanical strength was almost the same, but the brittleness was a little bit decreased. So these are the result which has been obtained for the membrane. And here what we have shown that the fixed ions which has been and provided the fixed channel, and through that channel the ion has been transported through that. So these are some results which we have obtained, and these results for any particular type of ion conducting membrane can be are promising and can be utilized in various devices, such as fuel cell or some redox flow battery or some reverse electrodialysis setup. So this was all. I hope if anybody has any question, you can go for that. This was all. So thank you.
Thanks a lot, Dr. Rahul.
Yeah.
So descriptive so wonderful presentation and keeping in time also. Now the session is open for the queries. If anybody have any question regarding to this presentation, or if he or she has any query which has been asked through Rahul, please unmute your mic and you can ask the question. Anyone, any query? I must appreciate two areas of your presentation. One, the diagrams were very fantastically designed. It was very good to. And secondly, I have some queries on some part.
Yeah.
First, you have mentioned that you have calculated N and mu, and based on that, you are trying to conclude that up to what concentration level we can go. So this N and mu has been calculated by which model? Because every, as usual, being a physicist, we usually referring three theoretical models like Rice-and-Roth model or Khan model or Shed and Gerd model. All these three models have different idea. If these all are based on different concepts. Which model we have to conclude this statement?
Actually, what I have observed and what I have read from various literature and books, that calculating diffusion value is vague. To get a clear picture from that is not possible, because it's just giving an imaginary value for the model which we have proposed, or which we have found out, which we have implementing inside that. So trusting that fully is not enough. So what I have observed from all this system, after getting a certain value, what we need to do, we need to trust our experimental data, what we are getting from the experimental data. And then if it is matching with the all these models, then it is good, because for particular system, some model can be fitted well, but for all system, it cannot. So those are the constraints. That's why trusting diffusion value or N mu is not always work for
many systems. Our model is basically applicable to gel type of polymer electrolytes. If we go over skirt and guard model, it is very well fitted with the temperature-based system. If you go with the Rice-and-Roth, it is basically on the space charge polarization method. All these all methods have different limitations. We will send that we have to rely on our data, and then we can conclude ourselves. Very right. Secondly, I missed something out of that. You have shown somewhere a fresh water and sea water calculation. What is that?
Actually, that is another type of device we call a reverse electrodialysis device. And in that device, what we do, in one compartment, we put high salinity water. In another compartment, we put low salinity water. And from that difference, a salinity gradient is generated. And that salinity gradient provide potential. And that potential we give the charge, and through that we generate electricity. So it looked good, but the thing is, we don't have an active site for that, because that instrument only can be placed where the river ends in ocean.
Right.
So that's the thing, but it's it's a good system to generate electricity where the ion conducting membrane or polymer electrolyte can be used. That is the only thing. That's why it is put here.
That's good. That's good. A good idea. I think Dr. Noor has something to ask.
I have question to Dr. Rahul. Thank you, Dr. Hamid.
Okay. Sure.
Right.
Go ahead.
Now I saw that there's some good display of picture, meaning that it's like you are doing a computational study also?
Yeah, we do some computational study. There are other groups who do this computational study. And especially we do molecular dynamic simulation on the particularly which are ion based. We prepare our polymer with a designed polymer, and we just give the structure to them, and then they introduce some ion inside that, and they see that how they are behaving.
Yeah.
That we are doing, but not high-tech one, but like a normal simulation.
I see. But what is the software that you use actually to
Actually,
simulate?
there are 2-3 software. So for molecular dynamics, I think some software is Gaussian. I think in paper we have mentioned that thing.
I see.
Software name also, and what the patches which we have utilized for that.
The Gaussian point.
Means that is one software,
That's
but we have used. I think I need to check. I need to check that software.
Because you also use Material Studio?
No. In Material Studio, we can design the structure, but we cannot simulate that thing. Actually, how we are doing, there is another institute which there's a universal institute here, like every country I think have. So we recharge from them. So they give that some 10 days time to simulate our data, because this has been done, I think, simulation done on, I think, supercomputer. Yeah. So they have those facilities. So we just put our data or this molecule, and within 1 day or 2 days, they give some parameters, and that parameter we are putting, and the graph which I have shown here, these graphs has been evaluated from that supercomputer only.
I see. Because actually, basically many software.
Yeah, there are many software.
Yeah, there's a lot of software, but basically they are focusing on the solid state materials. Mean that
solid. Okay.
Yeah, basically for polymer it's difficult to.
Yeah, it's very difficult.
Right? Yeah. Because the polymer, we have a big structure, and also the molecule is vibrate. It's not fixed at their place. So it's difficult, and we need to rerun for many times to confirm the results. Right?
So I totally agree.
Yeah, that's why I want to know what is the software that you use, so that maybe we can do some work together and can think the future, because it's better to simulate the experiment, the data first, then we try to do experiment. Right, so that we can save some materials, and also we can predict what is the output. Of course, it's not the same. Yeah. But we have an idea. Is it can work or not? Right, like what you did just now. So very nice talk and sharing.
Thanks.
Any more queries from participant sides? So there is no more queries, Dr. Rahul. So on behalf of IPS Academy Jhabua, I put my gratitude and thanks to Dr. Rahul for being present here and giving his valuable and wonderful talk on and conducting membrane. Thank you, Rahul, once again. And thank you, Noor. Dr. Noor is available and present to all of my talk. I am very humble and very thankful to Dr. Noor. He is a continuous participant to me, giving a very good support also. Thank you, Noor. Thank you. So
I always support you, Dr. Amit.
Welcome.
Okay, so I am closing here, and we will meet tomorrow at 11:30 with a talk by Dr. Neetu Kataria. And we have 3 more talks in this series, and then we will close. So long, I think it's an 8-day talk, FDP. But thank you, all the participants. They are being continuously present to us. Thank you once again. Thank you, Rahul. Thank you, Noor, and thank you all the participants. I'm closing for today.
Bye-bye. Bye-bye, everyone.